group theory, and today we'll be doing the group action. Um, so you have all seen the dihedral group, right? So this is the dihedral group is the group of rigid motions of a square which preserves the figure. This is our original the square in the first position. I call this vertex 1, this vertex 2, this is 3, this is 4. Then I change, I do a 90-degree rotation. This everything rotates this way. So 1 comes here, 2 goes here, 3 goes there, 4 comes here. So this is this. Then I do it once again, 180 degree, it goes this one. Then 270 degree, this goes this. And if I do one more, r to the power 4, then it will come back to E. No doubt about that. This one is another sort of rigid motion. This is the reflection about the vertical axis. Okay, reflection about the vertical axis. So 1 and 2 changes position, 3 and 4 changes position. So always compare from here. So 1 and 2 changes position, 1 goes here, 2 comes here, and 3 and 4 changes position, 3 comes here, 4 goes there. Now, if you combine S and R, then you get all the rest of the things. So then if you rotate it once 90 degree counterclockwise, then and you apply this vertical reflection, then you get the reflection about this diagonal, 1 3 diagonal. All right. If you apply the reflection after twice after 180 degree rotation, you get the reflection about the horizontal axis. And lastly, if you get this one r cube, after that, if you apply S, then you will get the reflection about this axis. Okay, this diagonal, 2 4 diagonal. Good. Now, the dihedral group is the group of rigid motions of a square that preserves the figure. Okay, abstractly speaking, this group is a part of the group S4. S4 is the group of all permutations of 4 elements, but actually is a much refined in the sense that this square, this figure, particular permutation belongs to S4 but does not belong to D8. Why? You see, 3 and 4 are keeping same, only 1 and 2 have switched sides. Okay, 3 and 4 are keeping same. Over here, only 1 and 2 have switched sides. Now, there is no possible rigid motion. There is no possible rigid motion which can transform this figure, this square, to something like this. You understand? You need to maybe fold only, take a piece of paper and fold only 1 and 2 and switch them, keeping 3 and 4 completely flat. Okay, so that is not an acceptable rigid motion. Acceptable rigid motions are rotation, translation, and reflection. Okay, so these are and the translation is not an acceptable rigid motion in this case, in this particular case, because we are looking for the symmetry of the square. If we translate, we know that in case of translation, there is no fixed point. Okay, so there is no way that the translated figure will be coincide with the original figure. So since we are talking about symmetries of the square over here, so rigid motions of a square that preserves the figure at that particular place. So the translation is also out of the question. So only possible rigid motions we have are rotation and reflection. So the square at the left, this is my original square, 1 2 3 4. The square at the left cannot possibly be made to coincide with the first square at the right, this one. So this belongs to S4 by a rigid motion. One needs an abstract permutation 1 2 for that. So this is simply an abstract permutation. 1 goes to 2 and 3 and 4 are remaining constant. Okay, this is a cycle in that notation. So one needs an abstract permutation, this particular cycle 1 2 for that. So this particular permutation belongs to S4, but this same thing does not belong to D8, that is the dihedral group. Okay. So why are we concerned? Because this group is a part of the group S4, abstractly speaking. Because what we are essentially doing in D8 are basically the permutations in some particular permutations with 4 elements. Okay. Nevertheless, S4 carries an isomorphic copy of D8 within it. A way to recognize that copy is carries D8 as a subgroup. Now, to trigger that subgroup is through group actions. How do we do that? That is our point over here. So we extrapolate the above idea in this paragraph. Consider any abstract non-empty set A. Let SA denote the set of all permutations on A. Okay, so this one, A is any abstract set. So A is, so you try to build the analogy. A is the set 1, 2, 3, 4. Then SA is your S4. Okay, A is not S4. A is the set 1, 2, 3, 4. Then SA is denote the set of all permutations on A. This SA is my S4. Mind it. We know that SA can be made into a group considering the binary operation on SA as the composition of functions. This we have already seen, right? The basic idea of a group G acting on the set A, I understand this thing carefully. The basic idea of a group G acting on the set A is to trigger permutations on A by the elements of the group G in a manner consistent with the group operations in G. Let's go back to this example of dihedral group again. So dihedral group has got two generators, and the generators are, and the elements are this way. That elements are this way. That E, R, R square, R cube, S, SR, SR square, and SR cube. These are the elements. Now each of these elements trigger some permutation in the set A, over the set A. So E is the identity permutation, nothing goes nowhere. My R. Then R square is which one? What? 1 goes to 3, 3 goes to, so 1 goes to 3, 2 goes to 4, 4, so this is basically 1 goes to 3 and 2 goes to 4. This is my this one. 1 goes to 3 and 3 goes to 1, 2 goes to 4, 4 goes to 2. This is my R square, and so on. So that means different elements of the group is triggering different permutations on A. All right. So the basic idea of the group G acting on the set A is to trigger permutations on A by the elements from the group G in a manner consistent with the group operations in G. Group operations means the binary operation in G. In this way, we will be able to find a copy of the group G in the group SA. Fine. With this motivation, let us define the group action as this. A group action of a group G on a set A is a map from G cross A to A. So I take an element G and I act with that an element from the set A and get back an element in A itself. Now understand, there is no structure there in A. A is a simple non-empty set. There we do not expect A to have any structure in it. What we are looking at to have a copy of G in the permutation group on A, in the group of permutations on A. So G is a group, G has a group structure, and it is trying to impose its structure on the group SA, the group of permutations on A. Okay, so a group action of a group G on a set A is a map from G cross A to A, written as G dot A for all G in element G from capital G and element small a from capital A, satisfying the following properties. What are the properties? The associativity property. For every G and G dash in G and small a in A, G times G dash times G and times A is G dash times A. Now realize this thing, that this dot group action, okay, and this between G and G dash, there is group binary operation from G. This dot is the group action of G acting on A, and this the dot over here, the multiplication between G and G dash is the usual binary operation between the elements of the group. Okay, so the associativity property must hold, and For every element A, the identity element will act on that element to keep it as it is. So E dot A is equal to A, where E is the identity element in the group G. Remarks. The first one is the abusing of the notation. We shall immediately become less formal and say G is a group acting on a set A, and the expression GA will definitely be written as simply GA, with the expected understanding from the students that this is not confused with the binary operation on G. Okay. A much better exposition on the motivation of the group action can be found in this particular article from MathStack Exchange. Okay, so let's say let's read through this one. Let's say we have a set of interesting things. For example, we might have the set C of faces of a cube, or the set R3 of points in Euclidean 3 space. To any set S, there is a group denoted odd S. This is what we are actually using, S sub A. That's to any set A, there is a group denoted by S sub A, S subscript A, which consists of all bijective functions F from A to A, where the operation is composition and the identity is just the identity function ID over A of small a is equals to small a. Okay. However, it's usually not the case that we care about every possible way of rearranging the elements of our set. Just like this one, this is not that much of an interesting permutation to us. This one does not correspond to any rigid motion. This particular permutation does not correspond to any rigid motion, whereas the rest of the guys over these things do. Okay, look at this permutation. This permutation is, or let's say this permutation. This permutation is 1 to 3. 1 goes to 3, 3 goes to 1. 2 and 4 remains constant. So this permutation is 1 and 3. This is the cycle. So this is 1 and 3. This much only. This one only. This is my SR cube. So SR cube is this one. So that means we are interested in some of the permutations and not all of them. So that is what he is writing over here. However, it's usually not the case. We care about every possible way of rearranging, that is permuting the elements of our set. For example, the permutation of C, that is C was the set of faces of a cube. Permutation of C swapping two adjacent sides and doing nothing else is not really as natural a thing to consider as the permutation of C that a rotation of the cube induces. All right. So swapping two adjacent sides and doing nothing else is not a very is just a twisting the entire thing, and it does not come as the rigid motion. But whereas the rotation of the cube actually a valid rigid motion. And there are tons of crazy ways of permuting R3 that can't even be written down. But we are mostly interested in mapping R3 to itself in geometrically interesting ways like reflection or rotation. This is my upper half plane. This is my lower half plane. And consider this x-axis. X-axis is keeping fixed. I am trying to take the upper half plane slanted to the right. Okay. So everything is getting distorted this way towards the right. And I do the same thing in the lower half plane, but to the left. Okay, I keep the x-axis fixed and I distort everything to the left. So in this way also the resulting thing will be bijective with R2. Definitely not a linear transformation, and this is definitely a bijection or permutation on R2, but something we are not that interested in. This does not serve any real purpose for us. So we are more interested in the linear transformations on R2 or R3. So those are the permutations. Those are the permutations we want to look at this point. So there are tons of crazy ways of permuting R3 that cannot even be written down, but we are mostly interested in mapping R3 to itself in geometrically interesting ways like reflection or rotation. Thus, we decide to restrict our attention to a certain subgroup G of SA. That is, in essence, a group action. We have a group G, each of whose elements determines a permutation of S. As I said, it triggers a permutation on S of A. This is as in the case of R3, we might decide in advance that that the only permutations we are interested in are bijective linear transformations from R3 to itself. Since after all, R3 has the nice vector space structure and we might as well preserve it. Then we are doing the representation theory. We have a group G. Each of those elements is assigned a linear isomorphism from R3 to itself, which thought of as a matrix is an element of GL3R. Now, sometimes we start out with the group G already in mind. Maybe it came up in a problem we are doing and we notice that there is a natural way that its elements can give rise to permutations on some set or linear isomorphisms of some vector space. Then what we have is not a subgroup G of this SA or G of GLNR, but instead of homomorphism, rho from G to that SA, rho from G to that GLNR. Okay, so this is the idea behind the group actions, what we are doing over here. We are trying to nitpick some of the permutations from the group SA. So let us first see how the above definition fits our objective of triggering a permutation by group element in a manner consistent with the group operations in G. Precisely, we want to prove this proposition. Let a group G act on a non-empty set A for an element G in capital G fixed arbitrarily. Define this permutation by G dot A. This permutation is defined via the group action. Okay, this group G is acting on the set A, so I am defining this permutation via the group action. Then the following effects hold that for every fixed G, sigma G is actually a permutation. That is, this is a bijective map for a fixed G. This is a bijective map. And the map from G to SA given by G goes to sigma G. Sigma G is a bijection, so that means sigma belongs to SA. So G goes to sigma G is a homomorphism. All right, that is what is meant over here. But instead of homomorphism, we will get over here. This one is a homomorphism, this map G to sigma G.